Okay, now we are going to do polar coordinates. Polar coordinates determine the angle and length of a vector rather than the position of the point on the rectangular plane. It's just a fancy way of saying that this is another way to describe an ordered pair. And that really is it. It is still going to be describing an ordered pair, a location on the XY axis. Polar coordinates rather than rectangular coordinates is just another way to describe the exact same location. I really want to stress that they are in fact, the exact same ordered, same location, a different way to describe them. Okay, so rather than how many units I go in the X direction and then how many units I go in the Y direction, instead I'm going to look at what is the angle I had to travel and then how far did I have to walk away from the origin. But it's still the same ending location. That is still going to be the end goal there. Okay, so we're going to use the letters R and theta, where R is called the radial coordinate. One thing to highlight there is that R really is the distance away from the origin in the XY plane. And then theta is the angle that you know and love from trig. So that really is going to be the same. So theta is the angular coordinate, which measures the angle whose initial side is the x-axis and then whose terminal side is wherever we're looking for. So we're starting with theta equals 0 is still going to be the positive x-axis. Okay, let's do a couple of examples here. So one thing I want to do before we graph these points is I want to label the x and y axes, because the main thing that I want you to take away from this is that this really is still the x and y axis. All I did, this is the regular x and y axis, it really is. All I did is I added these angles just to remind you where those angles are. You should already know them from trig. They're the same regular old angles that you know and love. They are just there as a reminder of where those angles are. So you really should be able to graph these without those angles ever being drawn at all. Okay. All right, let's keep going. So I'm going to look at the ordered pair. I'll start off with the point A, and then I'll do the point B and then the point C later. So A is the ordered pair 3 comma 5 pi over 4. And when I think of 3 comma 5 pi over 4, I really do mean the r comma theta, where r is going to be the distance away from the origin. So I'm going to go 3 units away from the origin, straight away from the origin, but I'm going to face the angle of 5 pi over 4. So I need to find the angle of 5 pi over 4. I have a few angles drawn for you to remind you where the angles are, but hopefully you know where the angles are. 5 pi over 4 is right here in the third quadrant. So that is the angle 5 pi over 4. And then now that I'm standing at the origin, like that's first of all where you are. You are standing at the origin, and you start facing the x-axis, and then you kind of turn around, and now you stop. Now you are facing the angle of 5 pi over 4. Then you walk 3 units away. So then I walk 3 units away. 1, 2, 3 units away. That's what those little circles are, to just help you walk 3 units. You really are just, you can get a ruler if you want to measure 3 units away. So that is the point that I'm going to label as A, which is 3 comma 5 pi over 4 in polar coordinates. Okay, let's do it again. The next one, let's do part B, which is negative 2 comma pi over 2. So for the, for the angle or the point B, negative 2 comma pi over 2. This is my r comma theta. So start with theta. It's always easier. It's just my recommendation. So I'm going to face the angle of pi over 2, which I have labeled there for you, but you should know where pi over 2 is, just like it was in trig. So now I'm facing the angle of pi over 2, and I'm going to walk negative 2 units away. Again, face the angle of pi over 2, and you're going to walk negative 2 units away. So negative 2 just means I faced that side, but I walk backwards 2 units. Okay, that's what the negative distance means. It means you walk backwards. That's truly it. You're just walking backwards. So now that gives me that point right here, which was negative 2 comma pi over 2. Okay, again, point C is going to be, I'll write it over here. There we go, 5 comma negative pi over 3, where that really is your r and theta. I still recommend you start with theta. Theta is negative pi over 3. So this is positive pi over 3. So negative pi over 3 is down there in the second quadrant. So I'm facing the angle of negative pi over 3. And I need to walk 5 units away. So I'm facing the angle of negative pi over 3, and I walk 1, 2, 3, 4, 5 units away, and that's where I am, 1, 2, 3, 4, 5 units away. Can you see how there is more than one way to describe that exact same point C? That exact same point could have been 5 comma 5 pi over 3. It also could have been negative 5 comma 2 pi over 3. That's worthwhile to notice because I could have been facing the angle of 2 pi thirds and then just walked backwards 5 units. So there is infinitely many ways that you can describe the exact same location. And it's always good to have more than one way to describe something because some patterns show up if you describe things differently. It's always a good idea. Okay, that's the definition of polar coordinates. And now we have some little bit of trig because as you can see, there was a lot of circles and angles. So of course we can throw in some trig. So to convert from polar coordinates to Cartesian coordinates and vice versa, it is worthwhile to notice what's happening for your polar coordinates. In Cartesian coordinates, if you ended up at the point x comma y, then x and y were the sides of a triangle. In polar coordinates, if you ended up at the point r comma theta, theta was the angle and r was the hypotenuse of that triangle. And so you can see that using Pythagorean theorem, x squared plus y squared has to be r squared because that really was just a right triangle. And then using SOHCAHTOA, you can see that tangent is y over x. We have that as well. Also using SOHCAHTOA, you can see that sine of that angle, SOHCAHTOA, would be y over r, which means r times sine of theta is y because all I did is multiplied both sides of that equal sign by r, and that's where I got the y equals r sine of theta. Similarly, using SOHCAHTOA for cosine, x is equal to r cosine of theta. These are four equations that you really are going to use a lot for this last part of Calc 2. And they're not going to be given to you. We really want to know those. And you can always just draw the triangle and do SOHCAHTOA, do trig from scratch every time. It's not too bad. Okay, let's do an example. Convert the point 2 comma 3 pi fourths into Cartesian coordinates, and then convert the point 1 comma negative 1 into polar coordinates. So this is a two-parter. We'll call that the part A and the part B, and I'm just going to break that page in half and do them one at a time. So for part A, I have the point 2 comma 3 pi over 4, and that is my r and theta, and I need to convert it into Cartesian. Cartesian is the same thing as rectangular. So I need an x equals and a y equals. So to do an x equals and a y equals, we have the equations. X equals r cosine of theta, which means x equals 2 times cosine of 3 pi over 4, which means x equals cosine of 3 pi over 4 is negative root 2 over 2. So I got negative root 2. And then I do the same thing for the y. Y is r sine of theta. So y is 2 sine of 3 pi over 4. And sine of 3 pi over 4 is positive root 2 over 2. So my ordered pair was x comma y, which was negative root 2 over 2 comma root 2 over 2. Ta-da. Okay, let's do the other one. It really is going to be that easy. So then for part B, very similar, except for we're working in the opposite direction. I am given 1 comma negative 1, and I need to convert that into polar, which means I need an r equals and a theta equals. This one's a little bit harder because the equations don't have an r equals and a theta equals, so it takes a little bit more work, but it's doable. We can do it. Start with the one that has the r squared. So r squared is x squared plus y squared, and I just replaced my x and y, which means r squared is equal to 1 squared plus negative 1 squared is 2. So that means r is equal to, when I take the square root, I get plus or minus. I have two answers. So I don't quite know the answer yet. I have two answers so far. Okay, that's all right though. We'll be able to figure it out. So that took care of the r squared equals x squared plus y squared. Now I'm going to do the tangent of theta. So tangent of theta is y over x. Tangent of theta is y over x, but my y is -1 and my x is 1. And then you have to just do a little like yoga for the brain. Really not yoga for the brain. You should know your unit circle. So tangent of theta equals -1 tells me that theta is negative pi over 4. Or all students take, let's see, it could have been also 3 pi over 4. There was lots of options here. Plenty of options. Maybe you chose 3 pi over 4. Like there's going to be infinitely many options. So 3 pi over 4, tangent of 3 pi over 4 is -1. And then here's what you have to do. I don't know if 3 pi over 4 goes with the positive root 2 or the negative root 2. You have no choice but to graph it. The point 1 comma -1 is in the second quadrant. Yeah, it's in the second quadrant, which means if I chose 3 pi over 4, which is already negative, oh, I'm so sorry. I'm so sorry. I probably won't re-record it, so I'm so sorry. 1 comma -1 is in the fourth quadrant. Here's my 1 and -1. I'm so sorry. 1 comma -1 is in the fourth quadrant, okay? And 3 pi over 4 is in the second quadrant, which means I'm going to face 3 pi over 4 and walk backwards, which means that would have to be the negative root 2. If I chose negative pi over 4, negative pi over 4 is already in the fourth quadrant, so that would have to just be walking forwards with a positive root 2. Whoo-wee. All right, we got it. Those are the 4 equations that you're going to use to convert between polar and rectangular coordinates. All right, there's always more than one answer for the polar. There's always more than one answer for the polar coordinate. Okay, let's do some more. Now we're going to talk about graphing a whole thing. So let's try to imagine this example really quick, and then I'll show you that in Desmos so you get a good idea of what it's going to look like. Try to imagine the curve r equals theta. Okay, r literally is by definition the distance away from the origin. R is the distance away from the origin. So if r is, and this is my xy axis, it is there. If I'm facing the angle of 0, I've gone 0. If I'm facing the angle of pi over 2, then I've walked 1.5. If I'm facing the angle of pi, then I've walked 3.14. And you can see that it's just going to get bigger and bigger and bigger. Let me show you that in Desmos. So the spiral is what we're looking at there. I'm going to show you that in Desmos. I think it is worthwhile to see. Let me just open up a new graph. So what if I were to graph, this is how you can do it in Desmos, r equals theta. And then you can see that spiral there, which I think is kind of cool. And it just keeps going around and around and around and around and around. Okay, so that's the type of stuff we're going to start to graph. And you should be able to graph these in your graphing calculator as well. You would have to change your mode. Before you go to your y equals, you'd have to change your mode to be polar. And then you can graph them in your graphing calculator. Okay, all right, so let's make a table of points, plot them, and sketch a rough graph of the following equation. So just like when we did parametric and I did the TXY table, I can do the R theta table for polar. I always recommend you start with theta. I just think it's easier. So you get to pick whatever you'd like for your theta. So I'm just going to choose, I don't know, maybe 0, pi over 4, pi over 2, pi, 3 pi over 2, and then I ran out of space. So I'm just going to choose those ones and see what happens. I actually don't know the shape of this graph. Let's find out together. If I plugged in 0 into the equation, r equals 8 cosine of theta, then r would be equal to 8 cosine of 0, and cosine of 0 is 1. If I plugged it in pi over 4, I would get 8 cosine of pi over 4, and cosine of pi over 4 is root 2 over 2, so I got 4 root 2. If I plug in pi over 2, I would get 8 cosine of pi over 2, but cosine of pi over 2 is 0. If I plugged in pi, 8 cosine of pi is -1. And if I plugged in 3 pi over 2, 8 cosine of 3 pi over 2, cosine of 3 pi over 2 is 0. Okay, so I've created a table of values. Let's plot those points. So first I face the angle of 0 and I walk 8 units. So I'm going to face the angle of 0 one more time. I just drew those angles there for you only, not because they're needed. They're not needed. Those circles are not necessary at all. I only drew those just to remind you where the angles are. That's it. Just to remind you where the angles are. So I'm going to face my angle of 0, which I know you already know where it is, and I'm just going to walk 8 units away. So if I walk 8 units away, then I ended up right here. And then I'm going to face the angle of pi over 4, and I'm going to walk 4 root 2 units away, which you can type into your calculator, is about 5.6. So I'm going to face the angle of pi over 4, and I'm going to walk 1, 2, 3, 4, 5, and a little. Okay, 5 and a little, and that's where I'm going to end up. And then I'm going to face the angle of pi over 2, and I'm going to walk 0 units. So I'm going to end up right there at the origin. And then I'm going to face the angle of pi, and I'm going to walk -8 units. So face the angle of pi and walk backwards 8 units, and I would have ended up right here. And you can kind of see I should have done a whole lot more points. I definitely should have. I only chose a few of them, but it ended up looking like a circle. Pretend I'm a good artist. All right. How do I know for sure that that really was a circle? How do I know for sure that that really was a circle? Let me show you. R equals 8 cosine of theta. Multiply both sides of that equation by r. And then I would get r squared equals 8r cosine of theta. You know what r squared is because we know that r squared is x squared plus y squared. So I can replace that r squared with x squared plus y squared. I also know that r cosine of theta is x. So then I ended up with x squared minus 8x plus y squared equals 0. You could complete the square for this guy, and that would end up being adding 16 to both sides of that equal sign. And I would have ended up with an x minus 4 squared plus a y squared equals 16, which of course is a perfect circle centered at center right here at 4, 0 with a radius of 4. So there's my perfect circle. Ta-da! Okay, let's do another one. Let's do some more. The next one is r is equal to 1 minus cosine of theta. I'm going to do exactly the same thing. I'm going to create a theta r table. I'm going to choose some easy numbers. I'm going to choose 0. I'm going to choose pi thirds. I'm going to choose pi halves. Maybe I'll choose I don't know, pi, and then maybe 3 pi over 2, and then maybe 2 pi. I'm just choosing some numbers. I always recommend that you choose them in numerical order. If you go skipping around, those dots are going to be very hard to connect. Okay, plug in 0. 1 minus cosine of 0. Cosine of 0 is 1, so 1 minus 1 is 0. Okay, and then I'm going to do 1 minus cosine of pi thirds. But cosine of pi thirds is 1/2. So 1 minus 1/2 is 1/2. Okay, pi over 2 is going to become 1 minus cosine of pi over 2, but cosine of pi over 2 is 0. Okay, and then pi, 1 minus cosine of pi, but cosine of pi is -1, so 1 minus -1 is 2. 3 pi over 2, 1 minus cosine of 3 pi over 2, but cosine of 3 pi over 2 is 0. And then 1 minus cosine of 2 pi, cosine of 2 pi is 1, so 1 minus 1 is 0. And I should have probably done more, and I'll show you how to do all of this as well in your graphing calculator to help you out. But 0, face the angle of 0, here's my 0. Face the angle of pi thirds and walk 1/2. Face the angle of pi halves and walk 1 unit away. Face the angle of pi, and I'm going to walk 2 units away. Face the angle of 3 pi over 2, it was 1, and then the angle of 2 pi was 0. And if I started to connect those, it looked like this little mini sideways heart. Let me show you guys how to graph that in your graphing calculator, because I think that might help everybody. If you've got your TI-80 something calculator, you can go to your mode. Mine looks a little different than yours, I know, but you can change it to, instead of a function, you can change it to polar, and then go to your y equals, and you can type in what you had, which was 1 minus cosine of theta. Theta will be the same button as your X button on your graphing calculator. And then I can go to graph it, and mine looks a little different than yours. I'm so sorry. Mine does look different than yours. Yours will look like that. There we go. That's probably what yours will end up looking like on your graphing calculator. Definitely pause and practice that in your graphing calculator. Okay, let's do some more. So now, instead of just looking at the graph in the graphing calculator, instead of graphing it using an r theta table, I'm going to try to eliminate all of my r's and thetas, which means I'm going to try to convert it into rectangular coordinates, which is the same thing as Cartesian coordinates. So those two mean the same thing. It doesn't matter which one you call it. They mean the same. Describe the curve as well. So what you need to do every time you're going to do a conversion between Cartesian and polar, you use the same 4 equations, which is x squared plus y squared equals r squared, tangent of theta equals y over x equals r cosine of theta, and y equals r sine of theta. Every single time. Use those 4. So, is there one I can use? Yeah, there sure is. R cosine of theta equals -4 just means that x equals -4. This is a vertical line. X equals a number is a vertical line. Cool. Okay, let's do the same thing for the next one. And again, I'm going to keep these same 4 formulas. I'm just going to keep them right in front of me because those are always going to be the same 4 that you're using. Right now, for part B, I have cotangent and a cosecant. None of those equations, those 4 equations, have a cotangent or a cosecant. So I have to get rid of the cotangent and cosecant first and turn them into tangents, cosines, and sines. So we know how to do that. We just have to manipulate what we have. So I've got now an r is equal to cotangent is the same thing as 1 over tangent. Cosecant is the same thing as 1 over sine. And then I can bring the sine to the other side of that equal sign, because now I will have an r times sine of theta. Cool. All right. So now I'm going to run out of space. Y equals 1 over, because r sine is y. So now I have a y equals, and then 1 over tangent, but tangent can be replaced with y over x. So y equals x over y, which means y squared equals x, which is a sideways parabola. All right, let's do it again. So I've got r equals 8 sine of theta. Same 4 equations that I need to use. I still need to use those exact same 4 equations. Those are never going to be any different. We're using all of those. So in this case, I'm going to do the same thing that I did earlier. I'm going to multiply both sides by r, and that will give me r squared equals 8r sine of theta, because now I have an r sine that I can use, and I have an r squared that I can use. So now I have an x squared plus y squared equals 8y. So x squared plus y squared minus 8y equals 0. Take the middle number, cut it in half, square it. That's what's added to both sides of that equal sign. And then we simplify from there. This will become an x squared, y minus 4 squared equals 16. That is definitely a circle that has the center of 0, 4 and a radius of 4. All right, let's do a little bit more. I'm going to do a couple of more graphs. What I'm going to do now, though, is now that you've seen how to graph that in your graphing calculator, I'm going to use my graphing calculator to graph this equation. 4 plus 4 cosine of theta. So I'm going to go to my graphing calculator. Make sure you've changed your mode to be in polar coordinates. And then when I go to my y equals, it might look a little something like this. Mine looks a little different than yours because I have just the iPad version, so I apologize, the wrong version here. 4 plus 4, forgive me, I don't remember what it was. It was 4 cosine of theta, 4 cosine of theta, and then I'll graph that. And you can see that it's also, whoops, this nice little mini heart on its side. Okay, so we can graph that. Cool. We have this nice little mini heart on its side. It looks a little something like that. Okay, not so bad. So what I want to do now is I want to show you some common polar curves. So I'm going to open up Desmos and I'm going to show you guys just some common polar curves that you might find really helpful to start recognizing some patterns, okay? So first thing I'm going to do is the sign. So you see right now what I have graphed is 1 minus sine of theta. Okay, and if I were to change that to be a 9 sine 1 times 1 minus sine of theta, you can start to see how that changes the shape of that graph. If you have a 1 minus cosine, it was the sideways heart. If you had the 1 minus sine, it was the regular heart or upside down. Okay, so those are some common ones. If I have the 1 plus sine, it's this upside down heart. If I have the 1 plus cosine, it's the sideways heart. Okay, if I have like a 4 plus 6 cosine, it's kind of like a heart, but it has sort of that little inside piece, that loop. It loops itself back around, which is kind of cool to see. All right, and then I have the same thing for the sine, but if that's upside down, you can still have that loop on the inside to see how that might look. Okay, then there's a couple of other ones that I really want to do. And I'm going to scroll all the way down. I'm just going to create a new graph here. There's tons here to graph and visualize. I just want us to see what things might look like. Let me do a quick guess here. Let's do r equals just cosine of theta. Okay, ooh, I should zoom in here. That should not be what I want. I want a theta. There it goes, then it'll pop up with theta. Okay, so there is my r equals cosine of theta. What if I were to change that to a 2 theta? Then I have this what's called a flower or a rose. This is a rose of 4 leaves. What if I were to change that 4 to be 5? Now this has 5 leaves. Well, let me go back to 2. When it was 2 on the inside, I had 4 petals of that rose. When it was 5 on the inside, I had 5. When it was 6 on the inside, I have 12. When it was 7 on the inside, I had only 7. When it was 8 on the inside, I had 16. When it was 9 on the inside, I had 9. So these roses, if it's even on the inside, you double the amount of roses. If it's odd on the inside, that's how many petals there are in that rose. So if it were 2, there's 4. If it were 3, there's only 3. If there were 4, there were 8. If there were 5, there's only 5. And so on. And then the same thing for the sine, but the nice part or the kind of cool part about the sine is it's just shifted 90 degrees in one direction. So it's still actually the same. It's just kind of cool. And it would be the same pattern too if it was, let's say, a 2 on the inside. Oops, oh, I forgot to write the sign. Sorry, there we go. What if that were a, let's say, a 2 on the inside, then there would be 4. If it was a 3 on the inside, there would be 3. If it was a 5 on the inside, there'd be 5. If there was a 4 on the inside, there would be 8, and so on. So these are some common polar curves that are really worth your time to just get the hang of the general shape. And so I have that link right here at the bottom to just check out some common polar graphs and use that to play around with, seeing if you can see some patterns. Okay, this last one that I'll do is graph the r equals a times theta. If a was 1, let's graph that one. If r is equal to theta, we already did that one, and it looked a little something like that spiral. But what if r was negative theta? You can imagine it's really the same thing, but now it's just kind of working backwards, right? Because I've got a negative theta. So I'm going to be working a little bit backwards on that spiral, going in the other direction. So I'd be going in this direction versus that direction. And again, you can use this link there. It's the same graph I was just showing you in Desmos to play around with the different common polar graphs. And then the next thing that we have to do is figure out all of the calculus for those, like the tangent lines, the area, the length, and so on. Okay, that's all we've got for polar curves. Thank you.